In this video, we're going to learn about equilibrium. So the first thing to know about equilibrium is that all chemical reactions are, to an extent, reversible. So here we've got the decomposition of mercury 2 oxide if we go from left to right, and it forms mercury and oxygen. But if we look from right to left, we have mercury and oxygen coming together to do a synthesis reaction in which they form mercury 2 oxide. So let's just say that we start off with a bunch of mercury 2 oxide, and that's all there is in a beaker. Okay, so let's say that we heat it up and allow it to start decomposing, at least to an extent. Well, initially, the rate of the reaction going forward is going to be as high as it ever will. There's a whole lot of HGO initially, and because of that, the rate of that reaction is going to be quite fast. There also is absolutely no Hg and O2 at the beginning. And so we're going to say that the rate of the reverse reaction of that synthesis going leftward is 0. Now, time passes. As time passes, the amount of mercury 2 oxide decreases because we're starting to build up more and more Hg and O2. So we slow down the rate of the forward reaction, and as there becomes more and more products, the Hg and O2, then the reverse reaction starts to speed up. And eventually, both of them level off, and the rates become equal. That is the state of equilibrium, when the forward reaction and the reverse reaction happen at the same rates. Another way to look at a sort of time graph of a reversible reaction is looking at concentration versus time. So here we have a case of concentration versus time where initially, yes, there's a lot of reactants and no products. And over time, there's fewer and fewer reactants and more products. This makes sense as the reaction proceeds forward. Now, in this case, well, at some point they're going to hit equilibrium. And note that the concentrations are not changing. Once we hit this point right here, this dotted line, once we get to this point, notice that the products are no longer increasing in concentration, they level off, and the reactants are no longer decreasing in concentration, they level off. What we can say is that the rate of the forward reaction and the rate of the reverse reaction are equal once we've hit this equilibrium point because there is no net change in reactants or products. But also we can tell that the equilibrium favors the product side because there's more products here than there are reactants. In the case of this reaction on the right, it's the same shape of graphs. The reactants decrease until they reach a constant, and the products increase until they reach a constant. But note that the equilibrium in this case occurs where there are more reactants than products. So we could say that for the reaction on the right, if we say that we have R at equilibrium with P, we can say that there are fewer products. So the reaction doesn't go forward very far, and the equilibrium favors the reactant side. On the other hand, in this case, we have the equilibrium favoring the product side because there are a lot of products and not many reactants. Moving on. Reactions may favor the products of the reactants, and so here is an example. We have water, and it breaks apart to form H3O plus and OH minus. And just looking at this reaction, it might seem, H2O is pretty stable. Then we build up charges on the other side. This is a reaction that doesn't go forward very far. There's a little bit of the products, there's a little bit of this, but you're always going to have a lot more of this reactant. And on the other hand, HCl is a very strong acid. So when it reacts with water, it breaks apart to form H3O plus and Cl minus. This actually is something that goes forward very, very favorably. It favors the product side with very little towards the reactants. So you're going to have a whole lot of this at equilibrium and not so much of this. Additionally, whether a reaction is favorable, part of it depends on what is going on, right? We talked about H2O breaking apart to form H3O plus and OH minus. That's just not a very favorable process. But also, favorability of a reaction doesn't just depend on what is going on, like what the reactants and products are. It also depends on temperature. And here we have an example. We have water as the liquid and water as a gas. Well, at 25 degrees Celsius, you all are fully aware that water will exist predominantly as a liquid. There is vapor pressure, so there will be some amount of vapor even at 25 degrees Celsius, but there's not a whole lot of vapor. There is quite a bit of liquid water. On the other hand, however, if we were to crank up the temperature to 150 degrees Celsius, that is well above the boiling point, there's going to be a whole lot of gaseous water vapor at a high temperature. And there's not going to be very much condensed liquid water at all. So this reaction, where we have water in the liquid phase boiling off, where that equilibrium lies depends very much on temperature. And that's the case with any chemical reaction. Temperature will affect the equilibrium position. As it happens, the boiling point is the temperature at which the boiling process becomes something that is favorable. So you can say that at 98, 99 degrees Celsius, the liquid water is still favored, but once you cross that 100-degree barrier, that's when the equilibrium favors the forward reaction of boiling off water. Anyway, that's all for this introduction to equilibrium. Hope this video has been helpful. Please feel free to leave any questions or comments in the comment section below. Thanks for watching.